have, last time, we have started to explore all these different things to say that some word actually, even in our language use, okay, it might have multiple meanings, okay? So when we just see something which is a mouse, the mouse actually could be referring to actually the animal of the mouse, or the mouse can refer to something which is in our computer technology that is used, a device which used to control the cursor or something, okay? And so if you have some system which take a mouse and always under that mouse to be an animal, then when we try to answer the question, then it's going to be given the wrong result, because when somebody asks something about where is a mouse, then you are actually trying to say, oh, I'm trying to find this animal. It's not going to be correct. Okay, so we need to have some way to be able to still kind of is in code, but it's not actually in code, but it's what we can call that to be the embedding, is to say that out of all these different meanings, okay, which one am I trying to say about this particular word? Okay, so sometimes even for the same sentence, it could be asked different ways. People could use different words to ask about the same thing. Okay, it could be asking something whether it has vanished or whether it has disappeared. So in the different sentence, when they use these two different words, but we know that if we can understand these two actually has a very high similarity, then in our model, we can actually use the same fact or the same knowledge to answer two different questions. One comes to ask when is it vanished, or the other one asks when it's disappeared. Okay, so to understand the meaning of each word, okay, which is to say that to be able to have the semantics of the word, okay, is going to be very important for the natural language processing, okay. And last time we have kind of introduced to these are different concepts that people have used to describe the relationship between words. Okay, some of them are synonymous, some of them are similarities, some they are related, some of them may have different connotation, which is meaning that in terms of the feelings, okay, how strong or how weak, and whether they care or they don't care. Okay, all these are different things which are quite important for us to understand in a language or in a sentence or in some article, so that we will be able to communicate, we will be able to answer the question, okay? And so for the large language model, these days, we often try to use some vector semantics to be embedding the word which is given to the model as the input. Okay, so what is a vector semantics? Okay, so basically for each word, we definitely want to be able to understand the meaning of it. But in terms of the computer, okay, how do we translate that meaning into numbers? Because computer, they can only process numbers, okay? So one way for us to try to understand some meaning about a word is actually to try to find out how it's been used. Okay, so when we understand the word by how it's used, is basically, we have mentioned about this, is that to try to understand what are the words around it, not just the word itself. If the word are used in the same way in two different sentences, okay, but they are actually used in the same way and they are supposed to mean the same thing, then we can say that these two words, probably they are similar or they are identical, okay? So if A and B, they are almost used always the same way, even in different sentences or in different contexts, okay? Then we say that, okay, if they are always used in the same way, then they should be synonym, means that they have the same meaning, okay? So last time we used this example to say that, okay, suppose you see this thing, term being used, onshore, okay, in somewhere in the text, and you have never seen onshore, this word before, but you can see that onshore in the sentence is describing to say this is always sauteed with garlic, or they are always something to eat over rice. Okay, and this has a leaf with something. And then if we look at in other different part of the article, or from our vocabulary, or from our corpus, that people have used this kind of description to say spinach is described in the same way, okay, or chard, okay, described in the same way, or color, described in the same way. Then we must say, well, onchoy probably is similar in terms of meaning, very similar to spinach, very similar to chard, okay, and very similar to collard greens, okay. And so we would like to be able to design a system that we can take any word and then convert them into some numbers. And that numbers, when they are similar, then somehow their numbers are related, or they are close to each other, okay? And so researchers have tried to come up with understanding to say, how do we discuss two words? Actually, they are similar to each other in terms of numbers, okay? And so one way is to say that, well, we need to be able to say each word probably has some different ways to be describing, their semantic, their meanings, okay? And this is in 1957 already somebody have designed some dimensions to say, how could I describe a word in terms of its affection, its effectiveness dimension, okay? So each word, okay, which can be, in terms of these three dimensions here, valence here, arousal here, dominance here, okay, we can try to see that this word is a score in that particular dimension, or very weak in that dimension. So for example, a nightmare, okay, and happy, they should be very different. So in terms of dimension, in that particular dimension, one would have a full score and the other one would have very weak score, okay? And another dimension, okay, one is frenzy and the other is napping. Napping means that you don't really care, and frenzy means that you are very, very eager, okay? Then, again, that they have very strong, very opposite meaning. And so therefore, in that particular dimension, one would have very high score and the other would have very low score, okay? And the last one here, so for you to compare between the leadership and empty, okay, leadership means that you have very strong kind of capability, okay, or you have very strong dominance, or compared with powerful and weak, one is very strong and the other one is very weak, okay. So if we can define the dimensions in terms of the semantics, and we use that dimension, then for each word we want to encode in our system, then we may be able to find some weight for that word to be in that dimension, in this dimension, and in this dimension, okay? Which is similar to like in the physical world, okay? We have our XY dimension, which is meaning that your particular street, your particular alley, or particular number or something. Then we also have the vertical dimension, which means how high you are, which floor you are particularly, okay? So by using this X, Y, and Z, we will be able to locate a specific person. So we want to use the same idea for each word we're going to process in a natural language. Can we somehow come up with some kind of dimension, and so that we'll be able to put each word in its specific location, yet they can include some meanings, okay? Each dimension can give us some meanings, and from that meaning, we can give it to say it's strong or it's weak or something. So if we can put every word in such a dimension and find a location for that word, then we can start to argue to say that whether this word and the other word, whether they are close to each other or they are on the opposite side of each other. Okay, so for example, suppose that I tell somebody to say that I am here, okay, I'm on the 14th floor of this building, and somebody said, oh, I'm here also, but I'm on the first floor of this building, then you know that by saying that you are on the 14th floor and first floor, even though your other dimension, your XY location is the same, but your Z is so different, then you are not so similar to each other. Okay. On the other hand, maybe sometimes you are in two different buildings, but you are on the same floor. Then even though your XY positions are different, but your Z is the same, then maybe you're actually pretty close to each other. If there is some way, for example, you can go, to the roof and you can go to the other. Okay. So by defining the right dimension, by giving everybody, every word to have a score, we can try to include the word's meaning in our dimensions or in our space for each word. Okay. And if we can do that, then even if we have some language or some word we have never seen before, like this onshore, we have never seen this onshore before. And somebody asked a question about this onshore, but somehow if our system can tell us, oh, onshore actually its location is very similar to very close to spinach, very close to chard, very close to these collard greens, then we probably can try to answer the question, okay, even though this is asking about onshore, even though we don't know what it is, but just because it is pretty close to spinach, we can try to relate it to say, oh, okay, you're asking something about the vegetable, there's something going to be have leaves and this and that. And so even though we have never seen this picture before, we can try to give some meaningful answer to imagine, say, oh, onshore actually is something like this. Okay, and so then your question wouldn't be so totally out of something that you don't understand. Okay, so the vector semantics is the idea, okay, that we want to be able to come up with some embedding. Okay, we want to define the meaning of the word as a vector. We want to be able to define such a space, then we can put each word in the specific location in the space, okay? And then from that, then we'll be able to try to have some implicit meaning of the word, okay, already understood by the model, okay? And then from there, then we can design our natural language algorithms to be able to use that, okay, to understand the meaning of that particular word, okay? So even though in convolutional network, we don't try to do this. We simply take each of this picture here as just the pixels. But in the natural language processing, we have this extra step. We want to be able to identify each of them, not just the code, but actually to define them to have some embedding. Okay, embedding meaning that we already assigned some meanings. Okay, and with that, then it will help our model to be able to answer the questions. Okay, so with word, okay, a feature is just word identity in terms of number, but with the embedding, feature is a word vector, and so for example, suppose that you find one word here in terms of embedding is a vector which is 35, 20 into 17 or something. And we see another word, okay, and this word here has a vector which is 34, 21, 14. Then we don't really need to understand the original word, but we can just look at the vector and we can see these two vectors, even though they are different, okay, but you can see that they are reasonably close to each other because each coordinate here is just off by one. When you have something off by one, means that they are probably similar to a certain degree, but not very far away from each other. Okay, so we can use something that will be able to generalize the concept to similar, but even though we have never seen that particular word before. Okay, so how do we do this? As I said, for some old study in 1957, they come up with these three different ways to be describing the word. Okay, the presentness, okay, the identity of the emotion, the dominance of some word is strong or weak, okay, in the field of linguistic study, actually, people have tried to come up with all these different way of classification. Okay. For you, suppose that you are trying to come up with this dimension. Okay, the variance of this different type of things. If I give you the group of students in the university, okay, for all students in the university, we need to come up with some kind of number system. How would you design such a number system? Each of you is a student ID, right? What kind of information you can defer or you can, kind of refer, you can try to derive from your student ID. What is the first characters in your student ID? Your first student ID right now? M, right? What does it mean? Master. So that's already the first dimension. M means master. For some of the students, if they are still in the undergraduate degree, what is the first word? Is a B, bachelor. And for somebody who is in the PhD program, what is going to be their first word? D. How about for professors? Do you know what is the first ID for us? First character? If you are designing the system, what would you use? D? Okay, that's one way, right? But what about secretaries? S for staff. P is not for PhD. P actually is for professional. Okay, but actually, in our university, we use D. For professors, we use D. All our staff also use D. Okay, so I don't know why they use D for both the PhD student and also the employee. Okay, but anyway, so you now understand. Okay, the first word. Okay, what about the next character in your ID? Is that 1, 1, 1, 4, right? Yours is 114, right? Some of you are, maybe different, but yours is one. Why is it 114? It's a year of your admission or the year that you enter the university, right? So you can see that 114. What is the 114? Because 114 is 2025. Because 114 is the Taiwan's year, okay, not the international 2025. Okay, so by looking at the 114, already we know that you enter university in this year, right? So you can see that the number system, okay, even though it is one string of characters, actually it can be divided into all different things, and each of the different things here actually can be meaningful. Okay, after 114 is what for you? What is a character? Huh? 6. Is everybody have 6? What else do you have? 4. Okay. So you were no. Well, in the past, it should be okay. Sometimes at like when I was a student, okay, actually it was the college ID, okay, and then followed, college ID, and then the department ID, the department in the particular college. And after that, then there will be the US real ID, your sequence in that group of students. And the sequence in that group of students, I don't know this university. In our, when I was a student, it's going to be depending on your other different type of criteria, maybe your score, maybe your selection, or maybe something. Okay. So when you look at the student ID or employee ID, do you look at that just a sequence of numbers? Well, in the computer, yes, we do. Okay. But on the other hand, just like I explained, the numbers actually can have meanings. Okay, you can actually have some, each of this dimension here actually have some meanings. Okay, and so for natural language processing, we also want to be able to come up with some embedding. And that embedding actually, by looking at these numbers, we can somehow get the meaning, get some idea about that particular word or that particular subject or that particular something. Okay. And we can randomly come up with different dimension, okay, and then just try to fit everybody in. But of course, that dimension needs to be descriptive enough to be able to cover all different concepts, okay? And that's the area for linguistic study. But for natural language, for our machine learning algorithms, actually, we don't try to be so smart, but we try to make it to be something that the computer can do without asking too many questions. Okay, which is to something to say, how can we come up with something by, if we can look enough data, then already we can try to come up with this kind of embedding, okay, which is to come up with some dimension system, vector system that will be able to put the meaning of each word in that particular dimension representation, okay? And there are two different kinds, which is, commonly used. One is called the counting of the embedding, simple count of the embedding, and the other one is more popular, which is called word to vec, okay? The counting of the dimension is something which you can see very intuitively. Let me just try to use this one here, okay? So basically, the counting dimension is this. We already mentioned that each word, the meaning of each word is going to be looking at its neighbors, looking to see that what appears to be close to. So if I say spinach, okay, then probably when we use the word spinach, it probably will be something that is talking about food or talking about some vegetable, talking about this and that. Okay, so by looking at your surroundings, hopefully we can identify the meaning of that. So we'll be looking at to say that for each word, what are the words that would appear to be close to them always? Whenever we look at a lot of the article or something, if we find this word, we always find something around it. Okay, then we say, oh, this one here and there, okay, they are probably related. They are always, kind of connected. So if we can try to do that, then we'll be able to say, oh, okay, let me just try to come up with some particular, say, for example, here. Okay, this is an example of 4 different sentences. Is traditional followed by a cherry pie, a traditional dessert. In some of this, article, you say often mixed, such as strawberry, rhubarb, rhubarb pie, and apple pie, and such and such. And then in another sentence, you will say computer peripheral and the personal digital assistant. These devices are usually doing this and that. Okay. Yet another sentence here says that computer, this includes information available on the internet. Okay. So without going into detail, but basically, if you look at this word information, then you can see all the words around it are something probably related to the meaning of the information. When we look at the digital here, all the words around it probably something is going to give us some hint about what this word is about. When we talk about something with a pie, most likely this is also going to be describing something about different kind of food. Okay, so we can be trying to look at, for each word, look at its neighbors or neighbors, depending on how many we want, okay, to look at. And then we can just do a kind of a calculation. Say, for example, okay, for the word cherry, okay, the cherry, A has appeared pretty close to it. Pie has appeared pretty close to it, but computer is not in here, okay? For strawberry, okay, we don't have A, we don't have a computer, but we have a pie, which is also pretty close to it, okay? And then for digital, you can see that A and the computer here, computer is pretty close to it in the particular sentence, pi is not related to digital, okay? And for information, A is in here, computer is also in there, but pi is not in there, okay? So we can try to, for each word, we can simply look at its surroundings and then just do a kind of calculation to see that which word appear to be close to them a lot of times, okay? And here you can see that for the cherry, okay, we have no computers around it, okay? But for the strawberry, we have the pi that is going to be here, okay, and also in here. So therefore, it is appeared twice. By using such counting, we can roughly get some idea the relatedness of that word and other words. Okay, already we will be able to come up with some number sequence. And the number sequence for every word, we can try to compare how close they are to each other. For digital and for information, because they have this common occurrence of the computer, so probably they both are related in the sense of the digital technology, which is about information, which is about computers. But for cherry and strawberry, even though if we may not know its meaning, but they all appear to be close to, you know, in terms of pie, they probably describe to be some kind of fruit or some kind of vegetable or some kind of something, okay? So this is called the, by counting to see that how many words, okay, and how they relate to each other, how they are been used together with some other things. If we read enough information, okay, if we have read a lot of information, a lot of articles, then we can come up with a table like this. Digital, in terms of computer, in terms of data, in terms of the result, they have pretty strong number, big numbers. Information in terms of computer and data, in terms of result, they have, you know, big number. But cherry and strawberry, sugar and pie, they will have a lot of strong numbers. Okay, so this is one way we can try to represent each word. To say that, okay, I'm not going to remember the word cherry, but I'm going to remember the sequence of numbers, and the sequence of numbers is going to be our vector. And from this vector already, you can see that we can try to refer to the relatedness of two words, because if they are all have big numbers in similar columns, that means that they are probably related. Okay, we can ask computer to do this for us. We can have the computer read a lot of articles, a lot of, you know, reports, okay? And we just simply randomly choose some of these words, okay? And then we just have them count of each occurrence. Then each of them, we can try to, you know, kind of show this kind of things, okay? So here you can have two different words. One is called digital, the other one called information. In terms of dimension of the computer and data, one is like this and the other like this, okay? And if you try to put the word pi in these two dimensions, where is it going to be? It's probably going to be very close to here, right? Because they are not related to computer, they're not related to data, okay? So already this kind of simple counting of how many times that they have appeared together with each other, okay, already can give us some meaningful representation, and that already captures some semantics, okay, already some meanings, okay, and the meaning, even though it may not be totally precise, but it does carry some meaning, okay. So this is actually one way for us to do it. Suppose we choose, you know, like some size of your vocabulary, like 5,000, then you can define this 5,000 by 5,000, you know, kind of metrics. Okay, each one of them would tell you how each of the 50,000 words is related to the other 50,000. Okay, and each 50,000 word can have some unique numbers. Okay, that could be one of your embedding. However, the problem with this is that there are going to be a lot of zeros, because each word is not going to be close to every word. So there will be a lot of words you're going to show that, okay, many of them are zeros. Okay, so even though you can represent it in this way, your vectors okay, most of the vector for you to be representing each word going to have too many zeros. You have some numbers, and even some numbers are going to be very small numbers, even if they are non-zero. Okay, so this is what we say that such a representation is pretty sparse because the matrix has 50,000 by 50,000 spaces, but most of them actually have value 0. Okay, and for computer technology, that means that you're wasting those storage for you to be representing those numbers. Okay, so the second way for us to be trying to describe the information in terms of the vectors to represent the meaning of the word is called word to vec. Okay, word to vec is not a sparse matrix, but it's a dense matrix. Okay, and word to vec is actually something that relatively we can have the vector size to be much smaller than, if you're using the counting vectors. In the counting vector, you need to have, big vocabulary in order for you to try to catch the meaning. But for vectors, we usually have something which is maybe 50 to up to 1,000. Okay, which is actually not quite true in the large language model, but this is possible to do that. Okay, so the word to vec is something that many of the large language model have been using. Okay, and these are some of the references you can find. Okay, but basically the meaning of the way for us to try to build the word to vec, okay, is actually not by kind of human to try to give them some way to come up with these dimensions. Okay, but actually is what we call the self-supervision. Okay, self-supervision meaning that you simply give a whole bunch of articles, okay, and don't even tell this computer to say which word they are supposed to try to build these dimensions, but just dump all of this to the computer, okay, and let the computers to learn by themselves, okay, and after you have, the computer has seen enough, and they can come up with some kind of, a result, okay, and then you simply say, okay, whether your result is good or not. If it's not good enough, then try to do some more. Okay, this kind of strategy called self-supervision, that the computer doesn't need human help to come up with this representation, is something that we like to use in most of our machine learning algorithms. No need for human to label them, but simply give the information to the computer, and then the computer try to train by itself. Okay, and so that is going to be a technology that we will describe, which is a word to vec. But since we're going to go into that, and so let's take a break first, and then we'll come back and we'll look at the detail of the word to vec. Okay, which exactly how they come up with the particular definition of the vectors, so that we can catch the meaning. Okay, let's take a break. Basically, that in the last lecture, I have motivated why we want to have a system that we can represent each word as a vector of numbers. And the vector of numbers, by looking at the value of that particular vector, we'll be able to try to understand, some semantics about the word. Okay, and we'll be able to say that even if we don't know the word exactly, by looking at its location in that particular dimensions, we'll be able to guess, or we'll be able to relate the word with something we already know, or we don't even really need to know that the exact meaning of each one of them, but we can see that how closely they are close to each other, and that to try to derive some information about the meaning of the word. And we talk about this counting each word in terms of its neighbors to see how many times they have appeared close to each other. But counting itself, is actually very, kind of mechanical, and also that it will create a vector to be a lot of zeros, because not every words are close to each other all the time. Okay, so there are too many zeros. So we would like to have some way that we can still provide a kind of embedding vector, okay, and we will be able to somehow, okay, find the for each word there will be some weight or some vectors that they have some meanings. And one of the most popular method that people are using, is the word2vec, okay, and there's another one called Globe, which is also very popular. And both of them actually that you can download the code from these places. And the idea here is that we don't want to do the manual counting itself, since we're doing the machine learning. So maybe we can simply ask the machine to come up with the model by learning, okay, from the data we have provided, okay. So by using some of this code, then we will be able to train a machine learning model, and then the machine learning model will be able to give us some kind of representation, not exactly counting, but predicting what, in terms of, if we give it some random space, okay, you will be able to put each one of them in certain location in that particular dimension or in that particular hyperspace, okay? And so in that way, we will be able to have the system to train by itself, okay? And we don't need to do the specific counting, and we don't need to have a lot of zeros. Now, how many dimensions should we have? We don't know, okay? The number of dimensions, again, is going to be something that we can just give the machine to say, I'm going to ask you to do it in 10 dimensions at first. You can ask the machine to say, I'm going to do 100 dimensions. And later you can say, I want to change it to be some different dimension. So you can decide the number of dimensions you want to have, and then simply counting, but simply to say, okay, I'm going to train you to be able to put a location, okay, to see that this word and that word, should they be close to each other or not? And how did the machine decide whether they're close to each other? By putting them in some locations, okay, randomly at first. Then we go through the text of the input and check to see that whether that initial assumption of their location, their distances, matches the distribution in your input. And if you input data in your input data, two words, okay, they are always far away from each other, then we need to know that, go back to modify your initial location and put them to be farther away. But if two words originally randomly we put them in two very far location, but then when we go through the text, we find that actually they are always close to each other, then we should move their location in the hyperspace to be close to each other. Okay, so that is the way to use the machine learning, is to say, I'm going to not tell you exactly where you should be, but I'm just going to give you something, and then I want you to tell me how to put them together, okay? Make it to be a prediction task rather than mechanically trying to do something, okay? So we can try to have the machine, okay, to do the self-supervision, meaning that I'm not going to tell them about the relationship between them, but here, initially, these are the words I want to be able to find a location, and you can randomly put it in somewhere. So when you go through the text I have given you, modify your location, and your location eventually matches the overall distribution of their distances in the text, then that will be the ideal location that is supposed to be. Okay, that's the idea of the word2vec. Word2vec is not for human to be doing something. Okay, so the approach is this. Okay, for each word, okay, something that is going to be what we call as a candidate word. Okay, is it neighbor or not? Okay, so suppose your word, which is a T, okay, that you want to be able to find its specific location, okay, and you have neighboring context word C, okay, and this two, in your original model, okay, you would assume that they are either close to each other or not, okay? So if you have two words, originally you assume that they are close to each other. That means that for other words, okay, which are not in this context here, they are negative examples. Okay, then for all these negative examples, the distance between them and your target word should be bigger than the distance between the C and the T. Okay, so if you have some words that they are likely going to be close together, okay, then you know that your value of the distance should be small. But for other words, they are not in this, then it should be big. Okay, so you can now compare between your original assumption, the distance between this and something else, and compare with the distance with, other words. Okay, and then you simply try to go through your assumption and check to see that each of the words that appear in the vocabulary to see that whether they match your assumption or not. And if they don't match your assumption, then you see that how much errors you have. Because you assume that these are supposed to be together and these are not supposed to be together. And if you go through the text, go through your input data, you find that your result is not right. Okay, then you go back and change your work. So this is the way for us to be doing all machine learning, is that by using some initial prediction, check your result, find your loss. When you have a loss, use the backpropagation to be updating each weight, each position, so that your location will be able to be match your specific things. Okay, so here suppose that we are looking at, because we cannot be looking at too long a distance, so we always need to define what is going to be our window. So suppose that we have an original word which is apricot, okay, and this apricot here, we are trying to find a location in the hyperdimension here to see that whether they should be close to some other words or not. And we find that this apricot here, it should be within some reasonable distance of tablespoon of and jam and egg. Okay, so now we have some initial target, okay, which is going to be apricot. And we have some initial context, which is going to be tablespoon of jam and egg. Okay, from that, then we'll be able to say, okay, the probability of this W and C, this is the W and this is the C, okay? This should be together, okay? We want to be able to trend this so that the apricot and jam, okay, are close to each other, but the apricot and this particular, random word is not going to be close to each other, okay? Then we can try to say, okay, now I know that this is going to be something that I want to be able to make my result to be the probability of this word to be close to the C should be bigger than the probability of W to be not within some word which is not inside of this context here. Okay, so so we can define some initial definition of your vectors. Okay, and then you just go through all the text here to see that whether your initial guess and your checking through the system, whether their result is very different or not. If they are very different, then you have big loss. Then you go back and then try to move their location. And when you move their location, eventually, if you have long enough, then you'll be able to find everybody to be in the right location. Okay, so we need to define, after all, we need to define that this to be something that we can compute. And so therefore we can define the W here to be a matrix and C here to be a matrix, meaning that you have some numbers that you can play with, okay? And we define the similarity between the dot values, okay? The dot product of these two matrices here, okay? Then you simply say, okay, now I'm going to define the probability for something to be close to something, okay, to be going to be the particular value, and which we're going to use the sigmoid, okay, and then by having this product value together, okay, it should be something going to be like a sigmoid distribution, okay, and then you can use this as a result you have for the positive, okay, And then for the negative, it basically is going to be 1 minus that. And so therefore, it's going to be your negative value, okay? And so you will be able to make the definition of, one initial result and, what it's going to be. It's a particular distance and whether it's going to be something that is going to be close to each other or not, okay? And then by multiplying all the words, okay, together, okay, to see that whether it's going to be similar to that particular word, then we can use this one here to define something that we can try to estimate, okay, the probability of W is going to be close to some particular word or it's going to be close to something, okay? So we will be able to define the location, okay, by defining the similarity. And from the similarity, we'll be able to try to use that for our machine to be trying to find for some target word, okay, and for their context words, and try to kind of adjust their specific locations in this context here, okay, and so that all of the words which are supposed to be close to each other is going to be moving closer and closer, and those something which is not important or to know each other is going to be moving away from each other. Okay, so let me just quickly show you that this is kind of the training we're going to do. Okay, so we have some initial weight, okay, and then we're going to try to go through the system to see that whether some word and some other words, whether they are supposed to be closer or not. If they are close, they are not far away, they are far away, then we try to move them closer. If they are not not supposed to be so close, then we're going to move them to be farther away. Okay, so this is shown in a linear form, okay, but you can imagine this is in a multi-dimensional form, okay, but in terms of distance, it still can be computed by this dot here, okay. So for each two words, okay, we'll define this way here, which is defining where they are supposed to be away, from each other, and by multiplying your particular C, your current location, with all the weight, then you'll be able to find out for each word, okay, how far or how close they are to each other. Then we'll be able to adjust each of the weight. Eventually, all the words which are supposed to be closer to you, they're going to be moving to be something closer to here. And for those things who are not related to your word, then they're going to be moving farther and farther. The theta here is to define their distance in the hyperspace. Okay, in the hyperspace here, you have this word and this word, okay? Then you'll be able to find their particular kind of angle which define the distance. Okay, by making theta bigger and bigger, then they will become farther and farther away. So that is just like here that you're showing that all the words is going to be moving closer to each other or farther away from others. Okay, and by doing this, then the word2vec will be able to kind of use the same idea of the gradient descent to see that your current location and your desirable location, whether they are, kind of right or not. We define the loss function, okay? And once you define the loss function, then you will be able to say, okay, I'm going to go back and adjust the weight, okay? And by adjusting the weight, then you will be able to eventually find the specific location, okay? So word2vec is to use the multi-dimensional thing and use the machine learning, okay? And then you simply build this classifier, okay? Just like we build this for the computer vision, we build a classifier based on some similarity between their vectors, okay? And if we assign each word some initial vector, and when we go through the whole text here, we find that actually they are always close together. Then we know that our current distance setting or our current location are not correct. Then we use that to go back to the propagation to update their weights so that these two will become to be closer. Okay, and if we go through everything, take all pairs of words, they don't give the negative example, then we can come up with the loss function to be updating the classifier in our training. Okay, then we'll slowly adjusting all of the embeddings. Okay, to improve the classifiers in the performance. Okay, and then eventually after we have go through this time and time again, okay, then we'll be able to find the specific location for each of the word in the hyperspace. Okay. After you have done that, then you can check the property of certain embedding, and amazingly that you can see that by going through some real examples of input text, okay, we can find that our embedding created for most of the words that we are familiar with, okay, and then compare with some other words they are related to, okay, you'll find that there are actually some analogical kind of a relationship between them. So for example, suppose that after you have done the word to vec, you'll find that if the apple is here and if the grape is here, it doesn't really matter how far away they are from each other, but between the apple and the distance to the tree, okay, from the apple, you use the same vector, use the vector from apple to reach the tree. And if you apply this vector into the grape, okay, so you take this vector between the apple and tree, and then apply this vector to the grape, then you will find that grape actually will point you to vine. Okay, so which means that you are embedded in that space. The relationship between apple to tree and grape to vine in your embedding space, actually, they are conceptually similar. Okay, that is the result of some, kind of a classical embedding. Okay, and people have done some study and they found that, from king and the vector to the man, okay, and you use the distance difference, okay, or the vector from king to man to applied to women, okay, then you will find that actually it's going to be close to queen. Okay, so the relationship between king and man and queen and women actually are in parallel. Okay, the same thing when you have Paris and France, and you're going to find that the difference between Rome and Italy is going to be something similar. Okay, which means the word to vec actually is able to capture some conceptual differences or conceptual relationship between king and queen, just like men and women, between France and Rome, just like, France and Italy, just like Paris to Rome, okay? And people have done more study, and here are some of the examples they have found. So you have all these different words, okay, and they may be in some space, but from aunt to uncle, okay, compared with niece to nephew, compared with sister to brother, okay, in terms of their vector, the relationship between them, they are actually similar, okay, and also men to women, and men to women, and sir to madam, heir to heiress. So you can see that in that particular embedding space, okay, everything from male to female seems like be this way to that way. The directions is going to be that way, and the distance-wise, they are similar. King to queen here, and you can see the emperor to empress. Okay, so all these different concepts here. Okay, Countess Dutch and Madame and the Queen, they may be far away, but their related word to other, which is have some male to female relationship. Okay, the way that they're going to be represented in this word to vec actually are almost similar. Okay, what is interesting is that people have also used the same training algorithm, okay, but try to look at some training data set from some old text to some more current text, Okay, and so what I found is that if a word gay appeared in some 1900, kind of a literature, okay, compare with gay used in a word in the 1950s, and compare with gay in the word, used in the 1990s literatures, they are actually in three different locations. Okay, even though it's the same word gay, but by looking at its neighbors, by looking at what it appears in the context, okay, in the word gay in the 1990s, okay, the literature appeared in the 1990s to be closer to all of this tasteful and things sweet and cheerful. But in the 1950s, okay, gay means bright, okay, and it's closer to this witty. But in the current literature, people use the word gay to be closer to lesbian, to be closer to homosexual, to be closer to all these different things. So even for the same word gay, if you use the classical way of encoding, they will appear to be this gay is the same as this gay as this gay. But when you put that into the word to vec training, because you'll be looking at this gay in that set of literature, which is in the 1990s, they are close to this happy and tasteful and such and such. So you would think that, oh, they should be belonging to be the same area. But if you read most of the literature in the 1990s, somehow they will appear to be close to all these other things. Okay, so that means the semantics actually is there. Okay, because it's the same word. Okay, nowadays, I guess for most of us, when we write our articles or reports, we don't use a gay to mean things like this. Okay, even though it's a very traditional way for us to be saying gay means happiness, but now most of the time when you use the word gay in your writing, people will immediately think that you are talking about, homosexual. Okay, the same thing. Okay, broadcast, same word, used in 1850 to 1900 to 1990. In the old days, broadcast means that you are trying to seed and sow, which is physical things that you are spreading things around. But then in the 1990s, it means newspaper and things like that. Okay, you're spreading not the physical thing, but the information around. So actually, the broadcast is being encoded or embedded in a space which is closer to the newspaper. But now, when you say broadcast, it's going to be radio. It's going to be something, because like we are using broadcast now, we don't really means that you're going to be spreading the seeds in the field. But we use most of the time when you say broadcast, it's going to be closer to radio, and BBC is one of the, of course, most well-known kind of not just radio but the media. Okay, for the current days. Awful. Do you use the word awful? Awful used to be means that it's awful means majestic. Only king and queen and things and you, or in terms of the in the religious text, awful means that majestic, solemn. You are worshiping this and that. That you are using the word awful to mean that you have such a high respect. But in the 1990s, awful means it's terrible. And now awful actually means wonderful. Okay, so you can see that, okay, this is what kind of interesting nowadays if you're trying to answer questions in your large language model. Okay, if you ask a sentence and if you use the word awful, the large language model needs to be very careful because you need to understand that when you use the word awful, are you using that in a very traditional sense or in a sense which is in that area? Or is that awful is going to be terrible, horrible, or is going to be wonderful? Okay, exactly the same thing, similar to awful. Another word is bad. B-A-D. Bad actually nowadays sometimes it means good. So when is bad is bad. When is bad is good. Okay. If you just use the syntax, just use the word, the character itself, you won't be able to tell. But you need to put them in the context. Okay, you need to be able to put them in the context. Knowing that you are reading the books from 1850 or from 1990, then you'll be able to understand what it's supposed to mean. And then you'll be able to choose the right embedding. Okay, and your embedding better match that particular context that it is supposed to have. Okay, and the Word2Vec, the software, okay, is able to try to give you such power, okay, by not just looking at the syntax, but by looking at your surroundings, by looking at your input text, context, okay, and then try to find which particular meaning it is supposed to be. Okay, so in the large language model, okay, all words, they will be converted into some coding, okay, and that coding by using the Word2Vec embedding, then we will be able to try to put them in the right meaning and can be asking the right question, okay. This is also something some people are very interested in research in research right now, is that how can we reduce the bias in our large language model, okay? Because suppose that, let's see, there was supposed to be another example, but maybe later we will see that, okay? But there are some if you look at some of the older texts, okay, the word embedding for competence, okay, are often used to describe toward men, okay, and also in some older texts, okay, dehumanizing this particular word, okay, actually, which is close to barbaric, close to monster, to bizarre, they are often quite closer to Asian. Okay, so that particular word, dehumanizing or barbaric or kind of bizarre in those words, okay, will be more closer to Asian than the Western people. Okay, but this is not so much anymore in the 20th century. In the 20th century now, if you look at some of these adjectives to be describing human natures, they are not so much bias used to describe Asian people anymore, but is more general. Okay, that is something that some people are very interested in studying in a large language model with a certain things, what we call as the gender or ethnic bias. Okay, with certain words be used too much towards certain races or certain group or certain ages or something. Okay, we want them to be probably back to the more, kind of a more non-biased way. Okay, which is just like to say that, for example, when we say gay, okay, nowadays the gay has been used to describe a specific group of people, but maybe the gay, should be more used more evenly to mean that a lot of times gay are just describing that you are happy, you are cheerful, okay, you are this and that, okay, not to be biased to be because certain word has been used in a very special way to be describing certain people. Okay. In United States, one word people need to be very careful not to use is Negro. Okay, Negro. Negro used to be just like gay, just like black, just like this. It simply is a description of black people. Okay, but in many contexts, because it's been used in a description which is toward kind of dehumanizing you to be closer to slave. So when you say somebody is a Negro, you immediately like pushing them toward they are the label of the slave. But the original meaning of Negro may not be that. Original meaning of Negro is just describing you are black people, you are from a certain area. But people need to be careful. And the embedding here actually can be useful for the large language model, but also the embedding here can be useful for us to be more careful about use of certain words. Okay, and that is something that actually is quite interesting. Okay, so now we are ready to move into the subject of large language models. Okay, large language models. So again, just like whenever we are talking about machine learning, okay, and the machine learning, the first thing is that you have your original input, okay, and then you kind of go through some encoding for the computer vision is you're encoding into some pixels, but then you go through the convolutional neural network and to try to find its some segmentation. And you can see the segmentation here, we already are talking about the semantic segmentation because we are trying to look at the picture to understand the picture, right? The semantic segmentation, the word semantic here means that we're trying to understand the picture, not in terms of pixel, but in terms of the area, in terms of the kind of relationship between them, okay? And so after that, then of course that, we can try to do more processing and then we can do this and that, okay? And then we also have mentioned a little bit about this idea of, kind of trying to downsample and upsample. Remember this? Okay, downsample and upsample. What is the meaning of downsample? Downsample is that we take some information which originally is the original resolution, right? Then we start to use the convolution. We start to make them to be smaller and smaller tensor or matrix or something. So the information content is going to be smaller and smaller. Then because when we want to do the segmentation, we need to go back to the original resolution. Okay, but here, of course, we still have this fully connected layer for us to be able to understand exact class of each of the pixel. But we have this downsample, and then we have upsample, so that we can go back to the original resolution. Okay, because we need to be able to see the picture in the original resolution. If we look at something in between, in the low resolution here, we wouldn't be able to figure out what is this. But after we have done the upsample, then we can see the relationship of the picture relate to the original picture. So this concept of downsample is to try to capture some important information Then upsample is to actually present that information in a way that we can, as a human, we can visualize, we can compare with the original input, okay, original picture, okay. This is the concept we can relate when we look at the picture, okay. For the large language model, it's almost like the same thing. Here, suppose I have, instead of a picture, I have a text, I have some article, okay? And so we want to create a machine so that the machine will be able to digest your information in a text and then somehow understand it, somehow capture the thing. Then when we do the upsampling, we started to try to find the answer to your question so that you human can understand the answer of your question. Okay, so that process of downsampling is to capture the meaning of your question. Upsampling is to expand the knowledge, okay, into something that you are trying to answer, is something that is defined to be the large language model. Okay, so large language model actually is simply a machine model, okay, which can interact conversationally with human, okay, using the natural language. So it's still AI, but now the AI is no longer just processing picture. AI is need to be able to understand the conversation, okay, understand the sentence that people have given to it, okay. So in the large language model, usually we have these 3 steps. Okay, I'm sorry that this is in the I have created a slide which doesn't have the Chinese, but somehow I have not put them in this computer. Okay, but in general, okay. So large language model, okay, or the machine, the AI machine that we're trying to create is to be able to talk to people, okay? And so what we're trying to do is to build this model, okay? Which usually what we do is that we need to try to gather the information, okay, from a lot of input text, okay? So we are no longer just look at one picture, but we're just like training using a large data set. Okay, so it's no longer just looking at one picture, but we look at many different pictures, and we try to train the model so that you can capture every picture's features. Okay, so in the same way, we first try to do the LLM pre-training. Okay, using self-supervised learning, meaning that we have our pre-training look at a lot of text, okay, from whatever you can collect in text in the human history or in the current human database or library, okay, and then try to train all of this into something that is powerful, that is able to understand what you are asking, okay. In addition, we try to kind of gather the knowledge, okay, in the network. So the next time when you ask a question, already you can understand your question, and already by knowing your question, already you can find some answers from the text you have seen before into something that you can say, okay, this belongs to here, and therefore that these are the area that is related to the question you are asking, and to be able to come up with the something. So usually we have the first step is a pre-training, which is to try to do the self-supervised. Don't worry about it, just take a lot of information. And then usually the second step, we would do supervised training using some target data set, which is to say, well, your original answer, okay, is general, because you have read a lot of the information, okay, a lot of input. But now I want to make sure that your answer is always correct. And so therefore, just like in the computer vision, so we give you some specific answers, correct answers that you're supposed to give. in your general model. So we have this fine-tuning step, okay, by using some supervised training, okay, using some specific target data set, okay. So after the two steps, okay, then we can come up with the model which already can first do some of the things, okay, such as you can um, try to hide some word in some original sentence and ask it to say, what should be the word in here, okay? And your model here, because you have read enough information, so you can try to associate to say that when you say open, when you say an account, okay, most likely this is going to be something about a bank. And so you can answer the questions to say, oh, there probably is a word bank in between, okay? So by looking at this open, by looking at this account, by looking at its location in the model, okay, so you have the embedding, you have the information, and by looking at all of the previous information, then you can find a lot of people when say open some account, it means bank. So therefore they can give you the answer to say, oh, it probably should be a bank, okay? So that's one way to try to use the information from the pre-training to be deriving the answer, okay, about something. Now, if you are trying not just to do this, but you are trying to be able to make some conclusion, then we probably need to have some, kind of more specific information to tell you to say, when I give you some words like it was a good movie, okay, all of this together, okay, they are not conflicting with each other, and probably they are trying to say this is a positive thing about this particular sentence, okay? And so therefore, in doing this, you cannot just go back and look at the text to say that, oh, is anybody using this and do something? We probably need to derive some information to say, oh, all these are good words and they are together. And so therefore they probably are positive. And usually you need to have some data set to let them know that all these words here, if they are together, is a positive comment, okay? And so therefore we probably need to have some specific data set, and then we can use it for the fine tuning, okay? So there are some specific technologies used when we try to build a large language model. There are many different details, and the technology is still evolving. And in the next class, we'll try to go through some of the general techniques for people to be general ideas for people to be building the large language model. Okay. So let's take a break, and then we'll come back to talk more about the large language model. Model. Okay, I think all of you have been using large language model. Okay, like it or not, that you are using many kind of software on your phone, on your PC, and maybe on your coding. And many times you are actually using some large language model. Okay, so large language model, the definition is actually quite simple. Basically, it's just simply you have, we are using the system which has text, and the text actually has a lot of information, just like in the earlier development of AI. AI is able to understand pictures, but now AI is able to understand text. Okay, and the thing about the language model is actually what we have just described. We have the encoding, and we have embedding. And from the embedding, we try to capture some semantics about each word, okay, in some hyperdimension space. And then by gathering the text or the words together, by collecting all of this semantics in the embedded semantics in the text, okay, we can see that learning from a lot of this text, okay, we hope to be able to capture the knowledge. Okay, but from the encoding to the embedding, we start to understand the meaning of each word. But by putting a lot of text together, now we are trying to derive the knowledge. And this is something is actually a very, very big jump. Just being able to understand each word of a sentence doesn't mean that we understand the knowledge behind the word. Okay, for human, we quite often you go to some talks and people would talk about certain subjects, and they will say a lot of things in your language. You understand every specific word, but when you have all the words together, do you really know what they mean? That is actually not an easy task. Okay, so the large language model, okay, the big assumption here is that we are able to process a lot of text, and somehow we are able to capture all the knowledge together in all these texts. That is in the old days that people don't think this is possible. So here, for example, suppose that you have some of these sentences with roses, Dalila and peonies. I was surrounded by something. We human, of course, will look at this one here, then you say, oh, okay, this is a flower. What kind of knowledge can you get from this? When you see this sentence, you notice describing that you can probably predict that, okay, you are being surrounded by the flowers. But when somebody says this, and suppose that you are supposed to give the next sentence, what would you say? What would you say is, suppose you're trying to have a conversation, you are the machine, and somebody said this, and you are supposed to give some response. What would you say? You know that some of the LLM trying to have the conversation, right? And so what would you say as a machine? Reasonable, a good LLM probably say, are you happy? Are you in a good mood? Okay, or some conversation would be say, do you want to buy them? Depending on what you want to talk about, right? Okay, but how do we go from here into next? And that would be the question of the LLM. Okay, the thing it's trying to describe here is that these are the things that the language is supposed to be able to fill in. Okay, so the model, the room wasn't just big, it was something. Okay, and that the large language model should be able to come up with this sentence here, this word here, enormous. Okay, but you could also have, suppose I'm the LLM, I would just say the room wasn't just big, it was gorgeous. Would that be okay? It's still reasonable, right? Enormous and gorgeous, big and gorgeous. They are still kind of related. And then depending on your context, it could, because if you could be describing, if you go to a palace, then you would say, oh, this room is not just big, it is really very well decorated. Okay, so it's not just enormous. Okay, the square root of 4 is what? 2. But you could also say something, give me some other answer you think you give. I can say not. Then what will be the next word? If I say the square root of 4 is not. Then the next word could be anything except 2. It's not 3, it's not 5, it's not something. Okay, because maybe the sentence before this one here, the person has described something, and then you are trying to answer the question, say the square root of 4 is not that. It should be this. Okay. So in the large language model, I think you probably have seen this picture also. It's basically a machine model. Okay, it could be transformer, it could be something, and we'll talk about the technology a little bit later, but let's just describe what is a large language model. The large language model is a neural network with some input, okay, which could be a context, could be a pretext, or could be a fix or something, and the output is going to be possible next words with some distribution, okay? So here is that you have input context here, so long and then for, and the next words, okay, the output here, in this model, it has said that, oh, given your context, these are the words, and I think the next word, the probability of this one, all is 0.44. THE is 0.33, and you know that. So all of these are possible outputs. But the language model here could actually have a whole list of possible outputs, and each of them would have some probability, okay, or distribution, okay? And the system, of course, need to choose one to be something that's going to be your output, okay? So if you give something like this, then you can have a model which will be able to continue to predict what the next word is going to be. If you choose here to be all, and because this one has the highest probability, then the next word that you can predict is going to be taking this whole thing together, add this word you have just said, and then THE should be the next one. Okay, just like when I give you this sentence here, the square root of 4 is, if I give you a not, then you shouldn't be followed with 2, okay, because that would be wrong. But if I not set 2 here, but I say is not, then you can say 3 will be the next one. Okay, so it's going to be depending on your input sequence from the beginning until now, or from certain place until now, and then the large language model, the ALM model, will try to predict what the next word is going to be. Okay, so in general, the ALM can have 3 different type of architectures. One is what we call as encoder, and the other one is decoder, and also something is encoder and decoder. Okay, the encoder is going to be trying to take all the information, okay, and then put them into the system. Okay, so the system actually would understand the relationship between them, okay, without outputting anything. Decoder, on the other hand, sometimes is usually going to be given some input, then you just try to produce the output according to the input. So we are using ChatGPT, we are using Claude, we're using Llama. We are always, most of the time, we are using the decoder because we are not doing the encoding. We are not producing the model. We are not training the model ourselves, but we are simply using the capability has been trained to produce the output. Okay, so we're using decoder. But we also can have models which actually, they could be trained and could be outputting at the same time. And it can be, kind of doing more and more. You will be training more and more as you go. So it will be some encoding and decoding at the same time. Okay, and that's why that in the industry right now, there are many different type of models. And some of the models actually are going to be more popular than others because they are decoders. Okay, most of the time, most of the system that we're using, they are decoders because somebody have already encoded them with a lot of knowledge in the language model. And so whenever we ask a question, then they can use the knowledge inside the model to be able to give us the answers. Okay, that will be the the decoder. And decoder, you can see that, of course, the GPT has many different versions, and Claude has many different versions, and Gemini has many different versions. Okay, but in the past, that when people at first that they often use a BERT and something to be built in the original model, which is they have the encoding. Okay, so when we say LLM right now, most people think of them to be just decoders because that's what they use to be able to generate some output. Okay, and in addition to just saying that you have the large language model, often also we go with also some generative model, which is able to, kind of continue the sentence, continue the input to follow with some kind of output, okay, and then can do this iteratively, generate output one at a time, and then you will be able to produce the output. So the encoders, on the other hand, is usually something that you are trained by taking a lot of information, okay, and then you'll be able to try to not just read the data in, but also try to guess that within those information, what are the information related to each other. And so therefore, if you have something that is missing, okay, then you will be able to predict that particular word from all the words around it, okay? And so therefore that you will be able to guess what's in the system, and that will be the knowledge that it has captured, okay? The encoder decoder is going to be training from one sequence to another, and this is going to be quite often used in machine translation, that you listen to some input, okay, and then using the information that is already in the system and also your input sequence, then it is able to output, okay, produce the language in another form, and so that you will be able to understand it, okay. Okay, so the conditional generation of the text in a large language model is what makes it to be so useful, okay? Because that we are able to train the model first, like we said, using the pre-training, and then once we have the pre-training, then we'll be able to predict, okay? Because we'll be able to have the system taking your input and then try to predict what the next one is going to be, okay? And you can think of your input to be some general information, or it could be some input-specific piece of text. So like if you have conversation, it's going to be, you say a sentence, and then the system try to say some sentence in response to your sentence. Or you could be asking a question, then the system will try to answer your question based on whatever is in the question, okay? And so the input, okay, that you give to a large language model, quite often we call that to be a prompt. A prompt is a question that is, before it generates something, you have some input sequence, okay? So here is a picture that you have your initial sequence here, okay? And then the system will generate some output, okay? So the prompt, it's going to be, first, of course, it needs to be translated into a token. And then you need to be able to find, for each token, find the embedding, okay? And then we give the embedding, then we give it to the model, okay? And then we'll try to, based on that, we'll compute the probability of the next token from all of the prior work that I've just shown you, that it has a model, then you generate all of the different possible words, and also what is the different possible the probabilities or score for each one of them. Okay, so sometimes that it could be that your sentence is not just to follow the next word, but it's going to be asking a question like, say, for example, the sentiment of the sentence, I like Jackie Chan, okay? And then it says is, then you're supposed to follow. Then this one here even though it is not in the form of a question, but it's just a sentence, but your language model should try to come up with a word of that. And if you can, to complete this word, okay, this one here should be defining to say, okay, it's going to be positive or negative. Okay, if your model look at this one here and say, oh, this one here probably is a positive, then you would decide to say, oh, is a positive, then what should I say? Okay, there are still going to be many different words. You can say this is positive, this is negative, or you can say this is good, or this is right, or something. Okay, so they can still have many different possibilities, and each of them you will have some probability associated with that. Okay, then when you ask a question, say who wrote the origin of the species? Okay, and then you can say convert this one here into like this. Okay, and then you give an A here means that you want the answer. Then the system would take this one here and frame that to be a probability question to say that if I have this sentence here, Q is going to be this, and then now you have an A after that, meaning that you are needing the answer, then what's going to be a probability for each of the word, okay, that could be potentially generate the answer, okay? And so this one here, you can see that from this large language model, it could produce the Charles, it could be of something, it could be something, and each of them would have a probability. And then you decide that which one you should use. Okay, so prompt is something is actually quite important because it's going to be used to by the language model as the input. Okay, and the input here will be used to somehow in a network in which we'll talk about the actual networks inside of the large language model. Then you would find the possible answers. Okay, and so the text string that the user issued to a language model, okay, is to do something useful. It's going to be something that would decide how the model will react. Okay, how the model will react. Okay, and so the skill of given the right prompt in order for you to get the right answer. Okay, is a kind of a in some tool set or in some classes it's called the prompt engineering. That is, think of the large language model to be just a machine, and this large language model it needs some input. Okay, and by using different input, okay, you will be letting the large language model somehow use the knowledge inside of the system, okay, to be able to come, go through different path in the network, okay, and then you will eventually come up with a different score, okay. So if you have a question, just like the human form, and if you put that into a Q in front of that, and then A colon after that, then the system will understand this actually is a question, okay. So a lot of time that actually you think you are asking a question, but from the language model's point of view, it's just input. Okay, it's just trying to follow your input with another token or another word or another sentence. Okay, and if you say that translate this, then because you have this particular translate in your sentence, then you will understand to say that, okay, I need to translate something, and this something here, will be identified, and the system will trigger different part of the system to say, okay, I'm going to try to translate something which is probably originally going to be inside of this single quote, okay? And then you need to understand that the Hindi here is supposed to mean another language, okay? And then you translate, according to the capability in the network, okay? You can also try to give your question to be something very specific to say that, do you think the input is a negative or positive sentiment? And you give them the choices, P and N, and then you think you would be something that's going to be generated. Okay, like I said, that if you don't give them this specific choice P and N, it may come up with something not just positive and negative, but you can come up with something more, kind of descriptive or more, not so specific. Okay, give you something generic. Okay. When you give a prompt, often you can also try to give it some demonstration. Okay, so here are the way for you to describe it, to say that if I have this, okay, then one, the answer would be this, and this one here, the answer would be this. Then you give them, this specific question, and you ask the system to say, okay, now, what is your answer? Okay, and the system will take all of this to be your example, and this example here will then give the context. Okay, and the context here would change some meaning about your school of computer science. Okay, because here we're just talking about this is school of computer science, but also we have this context here to say this is a high school computer science. So all this high school computer science and the question to get them some reasons for you to be, for the model to be searching for some specific knowledge part of the system. Okay, and then you will be able to answer the question given all of that context together. Okay, so prompt is quite often what we call as the context definition. Okay, prompt is not just a question, but prompt actually set the context. When you set the context first, then the large language model will be searching the area already close by to your context. You wouldn't be looking for other area. You will be very much emphasizing a specific area. And that would give you the answer which is closer to what you are looking for. Okay. So given the right context, okay, and also sometimes that you can try to have the system learn, okay, during its answer is something what we call the in-context learning, okay, and so the system will be able to try to use the example you have given in the model, which then try to come up with answer. Okay, next week we will be teaching RAG. Okay, the RAG technology actually is a form of in-context learning. Why do I say that? Because RAG is a technology which we have some large language model, okay? But RAG doesn't try to change the large language model. The language model is still the way it was defined. But RAG is trying to have the system generate some prompt outside of the language model, okay? But those prompts actually include some information, may not be in the large language model, or maybe it is something that is more specific than the language model, okay? And by using that, okay, then talk to the language model knows that whatever you said is already been given. So those are the context, and you will try to use that context to be trying to produce the output. So the in-context learning can improve the model performance, okay, but does not update the parameters, okay? So which is just like to say that when you try to use Python, a lot of time we use Python libraries. When you use Python library, do you change the Python language itself? No, right? Because the library is something outside of Python, okay? But if you define a library, which is a math library, for example, and if you have defined this SQRT, okay, which is supposed to perform the operation of square root. So your SQRT is defined first in context as a prompt. Then when you use your Python, when you say, oh, I need to do SQRT, then Python wouldn't go to its library, its engine or its capability. But you'll be looking at your library and say, oh, I found an SQRT there. So therefore, I'm going to use your SQRT to find the solution. Okay, RAG is like that. You are not really changing the model, but actually you have created an additional model. And this model is going to be in the form of a prompt, not in the library, not in the model itself, but it's going to be some outside of capability, okay, in the system. So therefore, when you ask the question that can be answered already by this capability, then the answer will be given. Or if that information that from your prompt can be used to help the large language model to produce some specific answer, that also will be useful because that is a form of prompt and to try to help the large language model to answer your question in the way that you have specified in your prompt. Okay, so the RAG or the prompt engineering is always the way that we are trying to increase the capability of some model and give our capability to be a priority for the large language model, okay? Or you can think of to say that because your large language model has been given some examples, and so therefore they will try to answer your question in the way that your example is showing, okay? So in that way, the answers will be similar in style, in knowledge level, in the context of something that you have defined in the large language model, okay? So now the next question that we want to ask is that when we train a large language model, how are we doing it? Okay. Right now, quite often that whenever we train a large language model, we have three different stages. The first stage is simply to do the self-supervised. So therefore, it has a lot of information. Then the system will try to just understand all of this by itself. It doesn't really, it's not really given any instruction, just say, here are the information, okay, read it. And so the system should be try to understand this, not in terms of the real meaning of that, but somehow in the pre-training, it is able to find how are the information related in terms of what we just like see, we're talking about embedded. From the embedding, you find this word, and these two words are close together, so therefore they probably are related. And then in some of the context, you find, oh, this word and this sentence, they're used quite often, so therefore this probably have some specific meaning. And then, then you have other things in one book. And if this book is a special book about biology, then probably a lot of information inside there, they are going to be related to biological fact, okay, or biological truth. So you will gather all this information and somehow in the pre-training, you put all of that knowledge inside of the model, okay? Just like suppose that we have a picture, okay, we have all this picture here, we train this and then we're able to, for each of the pixel, somehow is able to make a decision, what is the class? Okay, so after you have done that, you have all this information about each specific pixel, what is a particular class. But we are not asking any question yet. Okay, we're just saying that, okay, this is from what I have derived, these are the things. And does it know that this is a cow? No, it just said, oh, this is belong to the same class as something else. Okay, So in the pre-training, it's also that. It's going to be able to understand, not understand, but be able to classify all the information for the pre-trained data, okay? And then all of them are being structured in some way in the network. After that, then we can try to do the instructional data. The instructional data, they will be specific, true and false, they will be specific question and answers, okay? And so therefore that when you start to give them some examples, okay, you ask a question and what kind of answer, then the model will start to understand to say that this particular question, when I'm looking for the pre-trained model here, okay, I can find something related. And when you have this question, okay, and then I from my, you have this question and from my all the information I have, I think what follows should be this. And you can tell me whether it's right or wrong. And then if you say me wrong, then I'll try to restructure my model so that next time I won't give you the answer. Okay, so the instructional tuning here is to try to make it to be more specific, okay, in terms of the answer, because the answer you has learned from some of this may be not correct, okay, and so we can use the instructional tuning here to try to make it to be more correct. Okay, but here's this is still correctness. Finally, we can have the stage which is to say preference. If I ask you a question, then you can answer this kind of answer, or you can answer that kind of answer, because from both of this, I have in the past, I have learned to answer in different ways by using different probabilities. Okay, and so, but human, you can say, well, I like this answer or I don't like this answer. Okay, so you like or you don't like to the machine model, they both are correct because from their network they can come up with the answers. But human can give it some idea to say this answer is more preferred and this answer is not as preferred. And if you give them that, again, the preference here can be used to try to adjust your weight in the model so that your model, next time when you ask the same question, that it knows that it should try to give the answers in this way, okay? So this one here, instructional data, we can try to find some input data set, okay? It doesn't need to be human, but it could be from some correct exams, or it could be from some other information, and then that information can have such a structure. So therefore, this one here is going to be supervised, okay, because there are already some correct answer for each of these questions, maybe from some text, maybe from some exam material. So this one here still can be done by the machine if you have the training data set, okay, which is labeled. But this one here is often quite difficult for us to find such data set that you can say, I like it or I don't like it, okay, because to the machine, they are all correct answers. But human can give the preference to say, well, that's not the right way to say it. Say it in this way. And so quite often when we try to train the system, we need to have some human to be involved. And this is what we call as the human, with the human feedback. Okay, human will be there to make the decision to let the model know that what they have done here is prefer or not prefer. So prefer or not prefer is not really so much of correct or not correct. It's just a way for us to say, among all of the choices that you have given us, okay, we like this one. So please answer in a certain way, and the system can try to adjust its weight or your weights in order for us to try to be able to produce the kind of answer in the future. Okay, so pre-training is going to be the thing that we all know that right now that you involves a lot of work. Okay, not work by human, but a lot of work by computer. It's going to be reading so much information because when we're talking about large language model, Used to be that when you have thousands and then you have tens of thousands and you have 100,000 and then millions and now have millions and millions, and the amount of information we can learn in order for to train the large language model is getting bigger and bigger. Okay, and that is when we started to invent some technology so that we can handle such large amount of data. Okay, and transformer is one of the more popular model, but even transformer now there are different modification of the transformer to make it to be even more efficient and such and such. Okay, and so we just try to have self-supervised learning. Okay, try to take a corpus of text, some standard training data set. Okay, and just keep training the model using the gradient descent. Okay, to minimize the errors in its prediction. You give some input. Okay, when you produce some output, this output here you can check with your original text here and see that whether you match the text you have received in the training data set. Okay, so the self-supervised learning is mainly trained on many different data sets that you can collect it originally from some specific data set, but nowadays a lot of information from the web. Okay, and originally when people start to build a large language model, they just collect whatever information they can find, and later people found that it's not right because you are using a lot of copyright information, and so therefore that people started to try to collect information which they think that the information doesn't have any IP and they are public. Okay, and so therefore that one of the data sets called the pile, which can collect a lot of information without copyright from the academic publications, from the web, including the Wikipedia and such a Stack Exchange, and also from books, which actually there's no copyright. Okay, so the pile is a well-known data set that people now use to try to train the large language model. And there are always some information here. People are, kind of challenging that the information is not open, and so the set, even for example from the NIH or from the other things, okay, sometimes it will become to be copyright, or some of the information, for example, from the Wikipedia will continue to be changed, okay, expanding and some new information, and so therefore even this data set here is not always constant. So it's quite often that we continue to try to change it. Okay, there are some issues when we are trying to collect the data set. Okay, first is the quality, and second is the safety. Okay, because the quality, of course, is important because that once you put the information in a large language model, okay, you will use that to try to generate the output. So therefore, your input data set should have correct information. Okay, but safety is something that more difficult to do. Is to say sometimes that some information, okay, even though it is correct, but it shouldn't be included. Okay, because that sometimes that some information has some really bad information in there. Okay, sometimes that, for example, you have instructions for people to do wrong things. Okay, and you want to the large language model to avoid that. Okay, and also try to not use the incorrect information or unsafe information, so that the model doesn't seem as kind of biased. And from time to time, we see some of this news that people said that some organization or some company, they will say, oh, you are using some information without asking me. Okay, I have the copyright on the information, so therefore that you shouldn't do something. Okay, so there are always problems that when you try to train a large language model with your information has involved the problem of the copyright, okay, or the author is not giving you the consent, okay. Even it's an open website, maybe the website still have some information. The authors, no, the owners doesn't want to be included in their in the large language model. And also from time to time that we might have some private information. When you can gather from the website, doesn't mean that it is going to be always okay for you to try to include, okay, including some of the phone numbers and this and that, okay. Maybe sometimes you find some information with such information, but it doesn't mean that you should include that in the large language model, okay. And also sometimes that the information may have skew, meaning that the training data is disproportionately generated by author from the different places. So, for example, like we know that United States has large number of website and information, but it doesn't mean that the point of view from the United States is always correct. Okay, so how do we actually try to have the enough coverage of all the information source so that the model itself is not skewed, okay, not too much, has too much bias on that, okay. Fine-tuning is a process of trying to, once you have produced a model, and if you have some information that you can use to say, I'm going to try to make the system better by using this information, you can always do that, okay? And fine-tuning is similar to in the computer vision, the fine-tuning is that, you can try to have some supervised, okay, and then you put that information into the original model and see that whether the original model need to be modified to give you the right result, okay. And that is going to be something that depending on your specific task, okay, some of the fine-tuning is very important to do before you use it, okay, especially, for example, like in the medical area, that you want to make sure that even though you have pre-trained model, okay, but in a specific hospital, in some specific group of patients, you need to try to change the model a little bit so that you can give the right answer, okay, not always just the generic ones. So, for example, suppose you have some text large language model, which designed for the American patients, and you try to use that model for the Taiwanese patients, then you probably need to fine tune it because the amount of dosage that you use for certain disease should be, maybe not as strong. It should be lower and such and such. And so the fine tuning data collected from the local medical community is something that you need to do before you use the model for your specific medical purposes. Okay, so we give a general introduction to the large language model, okay, without talking about specific technologies inside of them, like transformer, like attention, like other things, which we will cover after next week. Next week, we'll concentrate on the built-in RAG models, okay, but definitely we'll come back to revisit the more specific technology for building the large language models, okay? And today we just want to give you some of the ideas about the architecture, about the general approach to be building a large language model, okay? So that will be our lecture for today. I'll still be here next week, but please bring your computers next week, because next week is not going to be just lecture. It's going to be actually doing some work, okay? Which then will be giving you some homework for this semester. Okay. Okay. Thank you.